anything about it. So basically, how I'm gonna start the presentation is by doing some examples, so you can like see the explanation before I actually write anything about before I write the theorem. I'm gonna go ahead and do the example. So you better love this matrix because you're gonna see it for the next 3 examples and won't change the matrices. So we're gonna suppose we have matrix A, which is a 2 by 2, and what we want is to find the determinant, and we want to see how operations with elementary matrices would change the determinant. So just so you know, the determinant for this matrix is 4. I don't want to, it's a 2 by 2, you can see it. 10 minus 6 is 4. So now let's do some elementary operations on it. So let's start by the first example would be, let's grab a matrix and let's multiply by the elementary matrix 0, 1, 0, 1, 0. So you know I'm just changing rows, so you're clearing that. So what's gonna happen is we're gonna flip the rows. Now our new matrix is gonna be 1, 2, 5, 6, and our new determinant is actually gonna change. It's gonna be a -4. So as you can see, if we switch the rows, we flip, we're gonna get a negative in front. So now our determinant is gonna be a -4 instead of a 4. Now for the second one, let's do another elementary operation. So we have our matrix A, and we're gonna multiply it by 1, 0, 0, 3. So all I'm doing is multiplying the second row by 3. Easy. So our determinant now is gonna be 12. Now that's a big jump from 4 to 12, but as you can see, I multiplied by 3, so the determinant was multiplied by 3. Easy. Now let's see the example, and last we're gonna do 5, 6, 1, 2. I'm gonna multiply by the elementary matrix. It's gonna be 1, -5, and 0, 1. So all I'm doing is multiplying the second row by -5 and then adding it to the first row. So that's gonna give us a matrix of 0, -4, 1, 2. So what do you think is gonna happen to the determinant? Is it gonna change or is it gonna stay the same? It's actually gonna stay the same. It won't change anything. So by looking at these 3 examples, we can get a theorem 3.3, which actually tells us what's happening in each operation. So
can I interrupt?
Sure.
I'd like to interrupt. It's just a matter of notation. A couple of things. If you look here, this is the matrix, and this is the determinant. The equal sign is improper here. You can say this is the matrix, therefore the determinant of this matrix will be 4. The same thing. You do row operation. This is the result. The determinant will be this one. So you can do that double error to say, therefore the determinant equals -4. It's just a matter of consistency in notation.
this is how the book actually said. Determinant of A is equal to 12. So determinant of A is gonna be equal to 4. So that's how the book writes it. So this, what it says is determinant of A. So that's the notation that the book uses. Now, the theorem goes like this. So we have row operation, and we have the effect.
I have a question.
Sure.
So, when you have these elementary operations, right?
Right.
You have to pre-multiply the matrix by the elementary matrix, yes, not post-multiply. For instance, in your example number 2, if you want to multiply your second row by 3, your elementary matrix 1003 should be before the matrix, yes?
Sure, that's right. Yeah, actually, that's my mistake there. So yeah, so these ones should be flipped.
I mean, it just happened that because
Yeah.
the determinant of matrices, the multiplication is commutative, you have the same result.
Yeah, it had to be. It has to be the other way around. Yeah, that's my mistake there. So this has to be the other way around. So it's the elementary times the matrix A. So that's the other way around. That's my mistake. It's just
So
I was trying to
yeah.
translate from the book to elementary matrices. Yeah, because I was trying to translate from the book to elementary matrices because in the book they tell you that they're using elementary matrices, but they don't show you the matrix. They just tell you like, oh, all we're doing is subtracting row 1 by row 2 by elementary matrix, but they don't show you the actual matrix. So I actually write it so you can see it. So this goes the other way around. So I can do that real quick.
Give us your best notation.
Alright, so before I start like rewriting all of this, I prefer doing it after so we don't lose any time. I'm just gonna give you the theorem so you know what's happening. Because with the theorem you're gonna understand it even if you don't have the examples. And
All right, fair enough.
so the theorem goes, if you go and interchange two rows, then the effect on the determinant is going to be the change of sign. The second one will be if we multiply a row by a constant, then the effect on the determinant will be multiply the determinant by the constant. And lastly, the third effect, the third operation will be add and multiply or multiply.
I have this. This theorem applies for 2
Oh.
by 2 or 3 by 3.
All matrices. That's a theorem for everything, for whatever
So you
operation.
interchange the rows. Let's say you have 3 by 3.
Yeah, you're still gonna get a.
Does it matter which one?
Doesn't matter. This is a theorem for all matrices, so it's supposed to work for everybody, for every single one. If I don't get it incorrectly. Yeah, that's that for the next. I'll do an example for 3 for a 3 by 3 next. So
So add and or multiply.
multiply of a row by another row.
So add or, because you have two ands over there.
Where
Add and or.
oh, and or like you can add. Well, yeah, but I didn't want to say like, oh, you have to multiply. No, you can add, just add them, or you can add and multiply.
Or the and, you have it written twice.
Or?
No,
No,
first
it's
one's
and or.
That's and or.
And
Oh,
or
sorry.
by another row.
Gotcha.
There's gonna be no change. There's no change on the matrix. So this is a theorem 3.3, and it should apply for every single row. Now, how is this useful? Well, let's see how it helps us. If you remember for the class from Patrick, from the class from Patrick, you'll remember at the end he said that if you have a matrix with zeros, like a matrix like this, you have a matrix with A, B, C, D, E, F, G, and with actually 0, 0, 0. If you have a matrix like this, your determinant is going to be just A, D, and what was that? And G. That's going to be your determinant, if you remember correctly from his class. So as long as
if you have a triangle matrix,
a triangle matrix. So as long as you can get these three numbers to be 0, you can get the determinant easier. So why is it important, the elementary operation? Because you can grab any matrix and just keep like getting zeros from it, and then you get the determinant. So it will help you for matrix from 8 to 10, or 8 times 10, 8, or any other matrix. So
What would the determinant of your example one be?
from this one,
Yeah.
it's just gonna be the multiply of A times D times G.
so this
That
is
was
an
in the last
example.
class. So this is not my example. My example is on G.
Just a request,
Yeah.
let's try to write matrices a little bit larger.
I wasn't trying to write that one. That wasn't my example. I was just explaining. Like the what Patrick explained in last class. So, so you want me to write you what he said? I don't think you need. Well, yeah, whatever. So, nah, I'll write in there. So let's have the example. We have 0, 2, 4, 2, 3, -1, -2, -3, and 6. So I do have every single elementary matrix that you need to use for this example, but I will explain it in the way the book does it before writing the elementary matrix. So what you're gonna do first, it is get a 0 either here, or just move a column or a row up, so you don't have a 0 here. However, you don't. What?
Can you read the matrix again, because it's so dense?
0, 2, 4, 2, 3, -1, -2, -3, 6.
Thank you.
6. Alright. So what we're gonna do first will be get a 0 in the bottom, because it's the easier ways. It's the easiest way to get a 0, and you don't have to do much. So in the book, just so you know, what they're gonna do is gonna explain it the same way as we have been getting zeros in the matrix. So you're gonna have row 3 is gonna be equal to row 2 plus row 3, or row 3 plus row 2 is the same. Those. So what's it gonna give you? It's gonna give you a matrix with a 0 in the bottom. So now we already have 2 zeros in the bottom. All we need is another 0 right here. So all we need to do is interchange row 1 and row 2. So row 1 is going to be equal to row 2, and row 2 is going to be equal to row 1. So we're just interchanging it. So our last matrix is going to be 2, 3, 2, 3, -1, 0, 2, 4, 0, 0, 5. So the determinant of this matrix is gonna be equal to just the multiply of these 3 consecutive numbers. So it's gonna be 20. However, remember we did a row operation right here that it was changing the rows, and I already said in the theorem that if you interchange a row, you have to add a negative sign. So you know you're coming with a negative sign, the determinant, from this step. So the determinant is going to be equal to a negative determinant. So it's negative 20 at the end. If you are wondering how to do it with the elementary matrices, so the first matrix will be this one. And the second one you move will be this one. So those are the 2 elementary matrices that I use in the same steps right here. So by interchanging, you earn a negative sign. So this adds to the determinant a negative sign. Now, the way I use this, and this is the main characteristic of the chapter, is because I actually don't remember if he wrote this, but a matrix A, which is X, A, Y, B, C, C, 0, 0, or X, Y, C, A, B, C with 0, 0, 0. For this kind of matrices, always with the triangular zeros here, you're always gonna get that the determinant is equal to X times Y times C. So this is the determinant.
So let's say we change rows like 2 times.
Then it goes back to positive. Because when you change, like the way they do it, when you do it by elementary algebra, what you do is after this step, you add a negative sign in the front, and then you know that you have a negative, and then when you interchange it again, then you add another negative, that's a positive. So now we have covered the first half of the chapter, but there is one last part, which is matrices and zero determinant, which is not hard. It's just like, when does the determinant is 0? I don't see it any complicated. The chapter really didn't do much about it, but let's just cover it anyway, so you know. So this gives you the theorem (3.4), which says if any of these conditions are gel,
Because you may want to underline topics, subtopics, and stuff like that. Yeah, if any of these, thank you. Conditions are
met. No, because if I say met, then you have to come, it's any. But it's just one. If any of this one, doesn't matter if the 3 or just 1. As soon as 1 happens, this happens. So if any of these conditions happens, you're gonna have a zero determinant. So let's start by the first one. The first one will be if a square matrix and any of the I'm sorry, I reread. Okay. First of all, you know to get the determinant has to be a square matrix. So the first condition is if an entire row or column consists of zero, the determinant is going to be zero. It doesn't matter what, it's going to be zero. Yeah. Yeah, I thought you had a question.
Okay. Oops. Does it have to be a square matrix?
It has to, because if you don't have a square matrix, you cannot get the determinant. So that's the first. The second one, if two rows or columns are equal, then it's still gonna be you're still gonna get a zero. So even if you have a 10 by 10 matrix and just two columns or two rows are the same, you get a zero determinant at the end. And then the last condition, or the last one that you're gonna get a zero, is one of the rows is a multiplier of any other row. You still get a zero. So it's kind of the same if they're equal, but you multiply them. So So pretty straightforward. I don't know if you want any examples of that.
If so could, like, you wrote one down, but could multiple rows and columns be like three?
If you if you have just one, then it's zero. Then if you have more than one, it's still zero. Nothing is gonna change.
I just want to make sure there wasn't anything weird that changed. Yeah,
No,
that were multiple.
So the general condition is that if any one row is a linear combination of all the rows, then the determinant is zero.
Pretty much. Yeah. And then if you have zeros in a whole row, then it's zero, because you cannot.
So if one row is a linear combination of the other, then you do that on the determinant matrices, and then you get your zero row,
And then yeah, pretty much yeah. Actually yeah, that's a good point. If you only like subtracting by each other, you're gonna get a whole zeros. So your whole zeros is just zero. Do you want an example of this, because that's pretty much the whole section 3.2. And then the examples that I have is just.
You gonna prove this by any chance?
I mean, if you want me to prove them, sure, but I think.
Interested in proving it, anybody?
I feel like it's pretty.
I mean, if you need me.
This is what Dr. P said.
He was talking about how all of
I
this.
heard the linear combination.
Yeah, how all of these are related. Like most of them just come back to this one, because if you multiply or subtract two rows that are equal, you're gonna get a whole row of zeros, and then a whole row of zeros is just a determinant of zeros.
Those of you took differential equation, it does it up with the Wronskian. We use Wronskian to check, well, we talked about linear dependency or linear independency. Remember, the Wronskian equals zero, then you have linear dependency between the state variables, y1, y2, y3, and so on. But what does it mean that determinant equals zero? It's exactly what Dr. P said. It's one row, in which one row is the